Electric power. You have three priming questions. What are the important equations and their respective units? What is a way to keep the power the same but reduce the current? And this will be one of your thinking questions. Think of it as understanding your equation. And then what is the difference in this power compared to the power we've talked about before? So, our equation, P is equal to E over T. This should look familiar to you. We used a different variable for the energy before in first term. This was work. Work was in joules. Work is energy. So power is equal to energy per time. This is the more generalized form of that equation that you learned before. Now, if we're looking for the energy, what does this equation become? So we're looking for the E, so we need to isolate the E. So our equation becomes E is equal to the power times the time. And there you go. You want to be able to manipulate your equations and move them around. A lot of these equations are simple 3, maybe 4 variable equations. I'm going to show you how we combine them together to get new equations. And it's not that things are new per se, but they are combinations of old concepts put together. So, the electric potential energy in a circuit is the product of the charge and potential difference. E is equal to QV. This was from the last video as well as from the last unit. V is equal to E over Q. Now, if we want to apply these two equations together, power is the change in energy per unit time. So P is equal to E over T. E, let me use a different color. E is equal to QV. So we're going to plug this in over here. So we have our QV that's going to be plugged in over there. So we get QV over T. So power is equal to QV over T. The charge times the voltage divided by the time. And this is nothing new. We are just combining some of our equations together. We're going to keep going further on in this. Going back to the last video, charge per time is current. If we rearrange this for the Q, we get Q is equal to I T. So the charge is equal to the current times the time. So if we go back to this equation that we just derived over here, where P is equal to QV over T, we can now plug this Q, let me use a different color now. We plug this in over here. So we replace this Q with IT, and we get this equation. P is equal to IV. You might be thinking, what happened to the time? Well, let's take a look. So we have a time here, and we have a time over here. This equation, let me write out the intermediate step here. We can say power is equal to IT V over T. You'll notice that we have two times. Oh, sorry, I should say a time on top and a time on bottom. These cancel out, which gives us the equation P is equal to IV. And this will be one of the main power equations that we're going to be working with. Now, we're going to go another step. Going back to Ohm's law, R is equal to V over I. If we arrange this, V is equal to IR, and I is equal to V over R. Now, we have our equation P equals IV. We can come up with two other versions of this equation by plugging in Ohm's law in a couple of different ways. So, if P is equal to IV and V is equal to IR, we can plug this V, let me use a different color, this into this V. So this becomes I times IR, which means that power is equal to I squared R. So P is equal to I squared R. Power is equal to the current squared times the resistance. And you've probably figured out what we're doing for the next one. P is equal to IV. Now we're going to be plugging in this version. Actually, let me use a different color now. We're going to be plugging in this version into our power equation. And so this is going to be for the I, plugging in over there. So this becomes, this is a substitution. So P is equal to V over R times V. We can simplify this as V squared over R. So power is equal to V squared over R. We've gone through a lot of mathematical steps, and it looks like we've learned a lot of new equations, but in reality, all we have done this entire time is combine our old equations together. There is actually nothing new for these equations. And if you can understand these equations, that'll help you for the practice problems. A stereo with a resistance of 55 ohms is connected across a potential difference of 123 volts. What is the current in this device? So we have our resistance, 55 ohms. We have our voltage of 123 volts. And we are asked to find the current. So we have V, R, and I, or IV and R. This is Ohm's law. So we have V is equal to IR. So we have 123 is equal to I times 55. So that means our I is equal to 2.2 amps. The next part is for power. What is the power through the resistor? Now, once we have our variables, we have our resistance as 55 ohms, we have our voltage as 123 volts, and we have our current as 2.2 amps. We can use any of our power equations that we have. And to remind you back to these, we have P is equal to IV, P is equal to I squared R, and P is equal to V squared R. In fact, you can use multiple equations to confirm and double check your work. I'm going to use P equals IV. So power is equal to 2.2 times 123, and this should give us 280 watts. And there we go. For this problem, this is your practice problem. Work on this, bring it to class, and check with the person next to you in class.